Welcome to Senior Design Tool Project. We are Group 10, and our team member consists of Michael Choi, Electrical Engineer, Graham George, Computer Engineer, Joy Weaver, Computer Engineer, and Ryan Flynn, Computer Engineer. Our project name is Pet Connect. What is Pet Connect? Pet Connect is an IoT device designed for automated pet door that use with existing sliding glass door. The main functionality is to open, close the door by using remote communication through mobile application. The motivation of this project is coming from one of our team members who had pet himself. He had encountered an issue to let his pet out when he had to away from home, which we believe that other pet owners also have the same issue as well. Pet needs some outdoor activities, but what happens if the pet owner away from home and leave their pet inside the house for a longer period of time? It can cause a pet anxiety and stress due to lack of outdoor activities. It's also increasing pet destructive behavior, such as chewing, digging, or scratching furniture. Also, the problem with traditional flat pet door is require cutting a hole in the glass, a door, or a wall. The limitation of pet size per a pet door flap, and also professional installation is may require. Goals and objectives. We want to create automated system to open and close the door. Also remotely control the device via mobile application interfaces. Sensors detection to notify users status of the device. Easy setup and installation to existing glass door. We want to keep the pet healthier by allowing outside activities. And finally, provide ease and convenience for pet owner while away from home. Specifications. We have 5 different requirements. Power usage is power to operate the system is value set at 80 watt. Sensor range is distance to verify the object. We use 24 inches detection for ultrasonic sensor and 18 inches verification for the RFID. The main housing would weigh around less than 10 pounds, and the main housing dimension is 10 by 10 by 8 inches. The budget for this project, we want to keep it less than $500.
Here we have our block diagram showing all of the different components of our system. We've broken it up into 3 sections. In the blue, we have the hardware, the red is the firmware, and the green is software. Next, we can see the system flowchart, which is a basic overview of how the user will interact with our home system and app. Starts off with the door closed, and then we ask, is the pet at the door? If it is, we then look to see what mode the user has the system in. There are 3 modes of operation that the user can change with the mobile app. The closed mode, which will just stay closed all the time. This could be used at night or for bad weather. The away mode is a solution to our proposed problem. It will send a notification to the user's phone displaying the live video feed and asking the pet owner if they want to allow the door to open. And finally, the home mode, which will open the door for the pet without the permission of the user. After the user closes the door in away mode or the pet comes back inside in home mode, the system then repeats the process.
Our product is powered by AC wall power. It is converted using the off-the-shelf AC to DC power supply adapter that supplies a constant 12 volts and 8 amps. Our product has 3 different voltage rails, 12 volts, 5 volts, and 2.3 volts. Our 12-volt power rail consumes roughly 60.8 watts of power and powers the motor driver, the electromechanical relay, and the linear actuator. Our 5-volt power rail requires 15.1 watts and powers the Raspberry Pi, its peripherals, and an LCD display. Our 5-volt step-down circuit has a power loss of 1 watt. Our 3.3 volt power rail consumes roughly 320 millivolts of power and powers the MSP430 and the LEDs. Like the 5 volt step down converter, the 3.3 volt step down converter circuit uses 350 millivolts of power at worst case. In totality, the PET Connect pulls 7 to 8 watts of power, which is within our product specification. This is the schematic for our 5 volt step down converter designed to output 5 volts and 3 amps. We have input capacitors, input decoupling capacitors. We have an inductor to regulate the current to the output. We have a voltage divider to send feedback to our IC unit, and we have output capacitors to reduce the ripple voltage. This is the schematic for a 3.3 volt step down converter, which is very similar to our 5 volt step down converter. It is designed to output 3.3 volts and 1 amp. The only difference between the 5 volt and 3 volt is our IC unit and the resistor and capacitor values of our units. This is the schematic for our home user interface. We have a 20-pin socket for our MSP430, LEDs, and we have an LCD display. On the left-hand side, we have the top side of our PCB layout. The top cluster over here is our 3.3 volt step down circuit. Towards the middle, we have our 5 volt step down circuit. And towards the bottom of our top side of our PCB is our home user interface. We have resistors on the back of our PCB for our home user interface to reduce the clearness on the top side of the board. Our J1 connector will supply 12 volts and 8 amps to the board. Our J5 connector is our USB Type-C connector that supplies 5 volt, 3 amps to the Raspberry Pi. And we have our J6 connector as our test connector and establishing UART communication from the MSP430 to the Raspberry Pi. For PCB testing, we first did a PCB bare board / continuity check, checking each node of the PCB bare board using a multimeter and matching that with the schematic. Once we populated the PCB, we did a power only test, testing each output node for 5 volts and 3.3 volts and ensuring that it's delivered, these powers are delivered to respective locations. For motor controller components, we require 2 components to facilitate communication to the Raspberry Pi to the linear actuator. Since the linear actuator is a DC brush motor, we need to change the polarity of the voltage applied to the actuator. So we need a H-bridge driver to control it. Due to the H-bridge driver's active low pin configuration, we require a signal relay to implement a open to close ground interface to allow the Raspberry Pi to control the motor driver, which controls the linear actuator. The diagram on the side depicts the circuit for the motor controlling circuit. The picture above shown is the first prototype board for this project. Upon testing and debugging, we noticed minor tweaks that need to be made. The following changes are improvements for later designs and revisions of the PCB. First, on the top side of the PCB, we can remove C13 and thus removing the red wire on the top left-hand corner, which is unnecessary. Second, the backlight of the LCD display does not turn on due to the 5 volt power and ground are applied to the incorrect pins. 5 volt needs to be applied to pin 15, which is pin A on the LCD display, and ground to pin 16, which is pin K on the LCD display. The current implementation has the powers of these pins flipped. Third, a pull-up resistor of 47K ohms is needed for the MSP430 chip to be functioning properly outside of the development launchpad. Lastly, upon inspection, the left-hand side of the PCB and the right-hand side of the PCB grounds were currently tied together. In order to correct that, a white wire shown on the back side of the board is used to connect the left side ground and the right-hand side of the ground, the PCBs, together.
One design approach we encountered was to address the computing and processing needs of PetConnect. Along with needing to run multiple scripts, our design incorporates both audio and visual data. To handle this needs, we chose the Raspberry Pi 4 with 4 gigabytes RAM. The Pi comes with 40 GPIO pins, which is more than our design requires for all of our I/O interfacing. This decision ended up being really beneficial to our project. We had little to no problems using the Pi, and we were also able to find tutorials to get us started with our code for the project. The second design approach I will discuss is physical security for PetConnect. With our design interacting with an exterior home door, we had to address security measures to ensure our users of PetConnect that it is safe. We designed PetConnect's housing and linear actuator to be placed in the track of the sliding door, where it will act as a security bar. So when the door is shut and the actuator fully extended, the door cannot be opened without either retracting the door or removing the housing from the track. We also integrated audio and visual security by adding a speaker, webcam, and microphone to the design. For the prototype, we chose the Logitech C270 webcam, which uses USB communication and has a built-in microphone. We also selected a small footprint USB speaker to fit in our housing. PetConnect relies heavily on sensors. In order for PetConnect to alert the user or operate the door, we required our design to detect an entity and then verify that it is an approved pet before proceeding. For entity detection, we chose an ultrasonic sensor. We had previously experienced using this sensor from Junior Design and didn't face any challenges implementing it into our design. For the entity verification process in PetConnect, we used RFID. The RC522 module we chose supported multiple communication protocols, as well as read and write operations. This module satisfied our needs for a functional prototype, but with its limited read range, we would choose another module or even a different verification technology moving forward. All testing for sensors was done with a breadboard kit where we connected them to the Raspberry Pi. For the ultrasonic sensor, well, once we had the code written, we looped it to get continuous readings. From there, we tested its sensing with multiple sized objects and in different environments. Once we were sure we had good readings, we decided on a range practical to a pet near a door and used that distance to trigger the verification process. For the RFID, we first tested that we could read the tags that we had. We then assigned one of the tags to be valid and one invalid, and made sure we could distinguish between each tag when read. We also implemented the process to time out and reset after getting no readings in 15 seconds. The last design approach I will talk about is our user interface. We want PetConnect owners to be able to see each process of the design in order to understand what is happening and help troubleshoot any problems they encounter. To satisfy this approach, we chose to include an LCD screen and LEDs to the housing of our design. To control all user face operations, we chose an MSP430. The G2553 was chosen due to its low power usage and it having plenty GPIO pins for our design. We determined that a 16:2 LCD screen and 6 LEDs were enough to display the design's operations, which are power on, entity detected, scanning ID, valid or invalid ID, and door opening or closing. Again, to test the user interface, we use a breadboard kit and connected all devices. Each operation of the design has its own function in code that controlled the LCD display and its associated LED. We also created an interrupt function that read communications from the Raspberry Pi. We first tested these functions individually, and then again with the interrupts enabled and a signal sent over UART protocol from the Raspberry Pi.
These are the software tools and programming languages that we use to create our system. The mobile app, Raspberry Pi, and the database all transfer data over Wi-Fi. We decided to go with an Android-only app because we thought it would be easier to access the development tools we need to create the app. That is Android Studio and Java, which the software team had some previous experience with both. The Raspberry Pi is being used to control the peripherals, so we also used Python 3 for that programming. We selected the Firebase real-time database from Google because it is cloud-hosted and provided an amplitude of guides and documentation that helped us get started. So more on the database, it allowed us to sync all of our components with the most up-to-date information. This was a priority for us because of the problem we were trying to solve. If the pet wants to go outside, it defeats the purpose if the user is notified of this hours later. Instead, when either the mobile app or the Raspberry Pi make a change in the real-time database, the other component will have the new data within milliseconds. So if the user wants to manually open the door from the mobile app, the database will be updated and the Raspberry Pi will see this change almost instantly and react accordingly. The diagram on the right shows how we organize the data, as we have three main subtrees in the JSON key value pair tree structure that the real-time database uses. Those would be users, pets, and activity. To test the database was working correctly, we used the Firebase console, which gave us the ability to see the database being updated in real time. The image on the right is a screenshot of this console. As you can see, are different branches that were mentioned on the previous slide. We started the test cases by checking the read and write operations to make sure the correct data was being passed from both the Pi and the Android app. Next, we focused on making sure that the time it took to see an update in the console was within seconds. Another major test was to ensure that with each read or write, only the specific data nodes were being accessed. We found that if a variable with the same name but different capitalization was attempting to update, then a whole new node would be created and cause errors and confusion in the database. We also referenced back to this console throughout testing the entire system, as it helped us to see what was going on with the data. Okay. As for how we transfer data between components, Raspberry Pi and Android both have libraries that allowed us to read and write to the database. That is Firebase, which is a third-party helper library, and the Firebase Android software development kit made by Google. To stream the live video feed remotely, our best option was Dataplicity. This is a technology that allows remote access to Raspberry Pis. Its tools of Hawkeye and Wormhole gave us the ability to securely stream the live video feed to a website. The mobile app programmers were then able to create a web view page that accesses this website and displays the live video feed in the app. This was a more secure and easier option than port forwarding the Raspberry Pi, because that would open up a user's private network to the public and would also require more configuration from the user. After the initial tests of the database read and write operations, we focused on the Raspberry Pi and the Android app, recognizing the changes in Firebase. Those would be the event listeners that are set on specific nodes in the database, such as is door open, is pet at door, and the sound variable. In the Android software development kit, event listeners are set to see the changes in the data and then react. In Firebase, they are called streams, but act almost the same way. So for testing, we changed one of the nodes in the database and printed a message on both ends. Once we saw it was working, we implemented the actual actions it needed to perform. To test the video stream, we used Dataplicity Wormhole, which provided the URL address to see the video stream in a web browser. We saw slow response times from the video when we used the Android Studio emulator, but this problem was solved when we tested it on an actual Android phone.
Here is mobile application flowchart. We start by verifying the user if they already have an account. If the user don't have an account, they're required to create an account, and their information will store in the database. If they have their login information, the Firebase database will verify their credential. When the Raspberry Pi detects a pet approaching the door, Firebase will get updated, and the application will alert the user by sending notification message. The user now can open the video camera and open the door to let the pet out. Mobile applications have three basic main screens. The first screen is profile screen. This is to display user information. Activity screen is to display history log. And the control screen, which showing the different mode of the application as well as current status of a pet and a door. Here is our class diagram. The user class will contain username, password, email, and the pet ID. Login register class, login validation class, activity log class, which contain date and timestamp, add pet data class, which contain the pet ID. The last one would be Firebase class, which contain the user object. Here are example of our user interface, and this is logo for the Pet Connect. The second screen is the login screen, and the third one would be sign up screen. The first screen, as you can see here, is the control screen. As you can see, three different type of mode the user can select from: the close mode, home mode, and away mode. Also, there's a radio button to show the status of pet and the door, and the microphone to allow the user to display different sound to the system, as well as the access to the camera. And this is the example of notification message, and this is the activity log from the activity screen. And here's just an example that the user can select different sound to play to the system. And here is the settings screen, which contains the user address and the map location. For the application testing, we have three different test cases. Test case number 1 is to check result on entering valid user ID and password. Test case number 2 is to check result on entering invalid user ID and password. This is the application should show the error message. Test case number 3 is to check response when the user press on login mode or button mode or the door button. Test case number 4 is to check notification response when the application set into away mode and when the pet is detected. This test case number 4 you should receive notification message pop up on mobile interface. Test case number 5 is to check result when the camera or speaker icon is pressed. And test case number 6 is to check result on activity screen if the log history is generated.
During the design process of Pet Connect, we didn't encounter any exotic standards to govern our project. For the PCB and hardware design, we used the standards for soldering, which describes the materials, methods, and verifications of such use. Printed circuit board, which governs acceptable hardware installation, and restriction of hazardous substances, which limits the use of such materials. For our communication design, we encountered standards for RFID, which governs the specific RF capture techniques, Wi-Fi, which controls computer communications and their frequencies, and data transfer, which describes the different types of data transfer and their encryption. To summarize our design constraints, for environmental, we made sure PetConnect had no emissions. Our economic constraints were the costs for prototyping and our end product, MSRP. The social constraint of our project was that it would mainly appeal to indoor and outdoor pet owners. Ethically, we would build our end product to last and to encrypt any wireless data. For health and safety constraints, we would reduce electrical hazards and employ redundancy checks and fail-safes into our end product.
The budget shown on the slide is the cost of one build of PetConnect. It costs a total of $376.94, which is well within our target budget of less than $500. Thank you for participating in our product review committee.